Can you listen to me? So, if you can listen to me, then let me start. Actually, for the past few days, my internet connection is giving a lot of trouble. So, if this goes on, we have to think of some other way for the rest of the syllabus. So, I don't know when it will start giving problem once again. Let's start. We shouldn't waste much time. Today, we are going to study about scaling and reflection in three dimensions. So, during the previous session, you have got some idea about three-dimensional space itself. Then we have discussed about translation and only translation. Right. Today we are going to study scaling and reflection. Let's start. We will start with scaling in three dimensions particularly. Now, if you can recall our discussion about scaling in two dimensions, then I can assume that you know until now what actually scaling phenomenon is. In computer graphics, scaling is a process of modifying or altering the size of objects. Before diving deeper, let we try to take a feel of the scaling in 3D space. So this is our Blender software. You can see one 3D object onto the on the screen, and this red line is your x-axis, this green line is your y-axis, and here is the option to do scaling. Let me select it. Now this is our scaling. Where is scaling? Rotate, move, transform, scale. Yes. Now let me grab the blue circle onto the x-axis and drag it. You can see that when you scale along x-axis, the x-coordinate values for different points in the object get changed, but no change takes place in y-coordinate value, and no changes are there in z-coordinate values. Now let me try y-axis scaling. We Yes. Now let me get hold of the tiny green square here on the y-axis and drag this along y-axis. You can see that the y-coordinate values get changed, but when you apply y-axis scaling, then no changes are there in x-coordinate and y-coordinate values. Let me try the same thing with z-axis. Now you can see that z-axis or z-coordinate values are changed, but x and y coordinate values have not changed. Another thing you can observe here is that when you apply scaling, then the object size can increase or decrease. So whether the object size will increase or decrease will depend upon the value of the scaling factor. Now I believe that you have get some feeling about scaling as a whole. Let me dive deeper. As we have observed, scaling may be used to increase or reduce the size of the object. Now, scaling subjects the coordinate points of the original object to change. We have observed in our example or our demonstration that the original coordinate values gets changed when you apply scaling transformation. Now, as we have discussed that when you apply scaling, the object size can increase or decrease, and scaling factor determines whether the object size is going to be increased or decreased. If the scaling factor is greater than 1, then the object size is increased. If scaling factor is less than 1, then the object size is reduced. So for this purpose, let we assume that we have a point object O which you need to scale in 3D plane. First, let we create our three-dimensional space. Yes. So this is your x-axis, this is the y-axis, and this is the z-axis. And as it has been stated in the description, initial coordinates of the object O which you need to scale is x-old, y-old, and z-old. For the time being, let us assume that this point is somewhere here. So its coordinates are x-old, y-old, and z-old. This is your original object O. Now, scaling factor for x-axis is Sx. Scaling factor for y-axis is Sy, and scaling factor for z-axis is Sz. And once you apply the scaling, then you will have the scale point at some other location, say O dash, and the coordinate for O dash is x nu, y nu, and z nu. So let me write it down. The coordinates for O dash is x nu, y nu, and z nu. So hope you now have get some idea of the entire thing, what is happening here. You have a point O which is defined by the coordinate x-old, y-old, z-old. Then you have scaling factor Sx along x-axis, Sy along y-axis, and Sz along z-axis. Then you apply the scaling and you get the scaled point O dash, and it is defined by the coordinate x new, y new, z new. So if you can recall the scaling in 2 dimensions, the mathematical formulations will be same here. And from your mathematical observations, you can say that when you actually scale along x-axis, what you do is you multiply your original x coordinate value with the scaling factor along x-axis. Similarly, to get the new y coordinate value, you multiply the original y coordinate value, y old in our example, with the scaling factor along y-axis. Then, for the z coordinate value after scaling, you multiply the original z coordinate value with the scaling factor along z-axis. So these are your equations for scaling. Now you need to derive the scaling matrix. For this, we will append the homogeneous 1 equals to 1 at the end of these original 4 equations. And if you convert these 4 equations into matrix form, you will get something like xn n zn 1. This is the vector representation for the transform point. Then you will have your scaling matrix defined like Sx 0 0 0 0 Sy 0 0 0 0 Sz 0, and last row for the homogeneous coordinate system 0 0 0 1. Multiplied with x old, y old, z old, and 1. So if you multiply the right hand side of this equation in matrix format, you will arrive at the same conclusion as has been described with these 4 equations. And this is your scaling matrix in 3D, HD 3D. So this was scaling. Here you have the equation once again, 3D scaling matrix. Left hand side represents the point after scaling in 3 dimensions. Then on the right hand side, first you have the scaling matrix Sx, scaling factor along x-axis, Sy scaling factor along y-axis, Sz scaling factor along z-axis, multiplied with your original point which you need to scale. So here we have a problem which you should try yourself by putting the values into the matrix. I hope you can do this. Now let me move to reflection in 3 dimensions. Now, from the general properties of reflection, we know that the reflected object is always formed on the other side of mirror. This is the general property or generic property of reflection. In our day-to-day lives, we see reflection in mirror. In reflection, mirror image gets created. And the second property is the size of reflected object is same as the size of original object. You know that reflection doesn't change the size of the object. Now, there is a little difference in reflection in 3 dimensions with respect to reflection in 2D. If you can recall reflection in 2 dimensions, you can remember that in 2D plane, reflection was performed with respect to some line. To establish the reflection matrix in 2D, we did reflection either with respect to the x-axis or with respect to the y-axis. But in 3D, as you cannot reflect a point with respect to some line or primary axis, you have to do the reflection with respect to some plane. Let me give this some thought. Why this happens? Say this is your 3-dimensional plane. Right? Here you have a point. Now give it some thought. Can you reflect a point in 3D with respect to some line, say primary axis, x-axis, y-axis and z-axis? It is not possible because in 3D a line or orientation of line is arbitrary. Or more precisely, what happens? Let me reflect the point P with respect to x-axis, then your reflected point will be somewhere here. Then you can see that if you join P and P dash, then the angle, this angle is basically 180 degrees. So if you can imagine this, you can find that you cannot do the same thing for reflection purpose in 3 dimensions. Rather, you have to reflect a point in 3D with respect to 3 primary planes as we have defined in the first tutorial of this set. Say, now you can reflect this point P with respect to xz plane. If you reflect this point P with respect to xz plane, you will get the reflected point somewhere here, or you can think it like in another way. The original point P is on the positive side of z plane. When you reflect this with respect to z plane, you will get the reflected point on the negative side of z plane or negative y-axis, along negative y-axis. So now I think the idea of reflection in 3D is clear to you. Or as you have to define a 3D space in terms of primary planes, and the visualization gets more clear. Now let me try to reflect this point P with respect to YZ plane. So you can draw your YZ plane like this. When you point, let me make it red color somewhere here, P W dash. In this case, you can see that the x coordinate value have not x coordinate value have only changed. There was no change in y and z coordinate values. And similarly, when you have reflected with respect to the xz plane, then there was change only in the y coordinate values. You can see that if the y coordinate value is y for point P, then if you have reflected it with respect to the xz plane, then the y coordinate value for P dash will be minus y, and x and z coordinate values will be same. So this was the basic idea or basic visualization for reflection in 3D. Let me try to establish them mathematically. First look at the statement. Consider a point object O which has to be reflected in a 3D plane. Initial coordinates of the object O goes like x old, y old and z old, and new coordinates of the reflected object O after reflection is x new, y new, z new. As we have discussed in 3 dimensions, there are 3 possible types of reflection. Reflection relative to xy plane, when only the z coordinate value will be changed. Reflection relative to yz plane, and in this case only x coordinate value will be changed. And lastly, reflection relative to xz plane, and in this case only the y coordinate value will be changed. Now let we look into them one by one. Tasks are simple. First, reflection relative to xy plane. As we have discussed, when you reflect something relative to xy plane, then only the z coordinate value gets changed. So x new will be equal to x old, y new equals to y old, but z new will be equals to minus z old. Where is the diagram? Yes. Let me draw it. You are doing the, let me take this another page. X, Y, and Z. Now you have to reflect the point O with respect to this XY plane. So the reflected point will be on the other side of the z-axis. So if you have a point P somewhere here, after reflection it will get it here, P dash. Now you can see that only the z coordinate value has been changed. It was on the positive side of the z-axis. Now it has been transformed to the negative side of the z-axis, and x and y coordinate values are unchanged. So this was the justification for this last line. Now if you want to convert everything to homogeneous format, you have to append 1 equals to 1, then convert this to matrix form, and you will get the reflection matrix relative to xy plane like this. If you multiply the right hand side, you will arrive at the same conclusion as we have been able to arrive using these four equations. So this was reflection with respect to xy plane. Now let me try the same thing with respect to the yz plane. When you reflect something with respect to yz plane, only the x coordinate value will get changed. You will get the x coordinate value on the other side of the x-axis with respect to origin. So x nu equals to minus x old. Y nu and z nu are unchanged. You can see it here. Let me zoom it. Y nu equals to y old, z nu equals to z old. If you convert this to matrix form, you get something like this. So if you multiply the right hand side, you will get minus 1 multiplied with x old, 0 multiplied with y old, 0 multiplied with z old, 0 multiplied with 1 old equals to x minus x old. Y nu equals to 0 multiplied with x old, 1 multiplied with y old, 0 multiplied with z old, plus 0 multiplied with 1 equals to y old. So y nu equals to y old. Similarly, you can compute the value for z nu. So this is your reflection matrix in relation to yz plane. You can see that only the x coordinate value gets changed. Lastly, let me try to derive the reflection matrix relative to xz plane. When you reflect something relative to xz plane, you can imagine from our previous discussion that only y coordinate value will get changed. There will be no change in x and y coordinate, z coordinate values. You can see it here. X nu equals to x old, y nu equals to minus y old, z nu equals to z old. If you want to convert this to matrix form, let me write 1 equals to 1 after these three equations, and you get the reflection matrix relative to xz plane like this. You can see that only the y coordinate value has been changed. So this was the idea of reflection in three dimensions. Now is the time for the quiz. So as we did in our previous sessions, we will do the quiz in connection to today's topic. It is not yet live. I'm going to make it live. It is 10:46. You have to complete the quiz in 15 minutes. So you can find it in Google Classroom. And at the same time, I'm going to share the link into the chat box. So the quiz ends at 11 o'clock. This is the link for the quiz. Yes, this is the link for Google Classroom. And from this link, you can directly access the quiz. So start. The questions are simple. It's not going to give you much trouble. See how you are doing in the quiz. So we have got our first response for the day. Second response. 5 more minutes are there. Rahul Satvik, 20 out of 20. Then Shoikot, 20 out of 20. What's this one? 62021. Only 2 more minutes. So those of you who are not done yet, be quick. So it's 11 o'clock in the morning, and as of now, I'm going to toggle the accepting responses button. You can attempt the quiz later on. Let me start our discussion first. Let's write down. Okay, fine. Let's start. Scaling subjects the coordinate points of the original object to change. The answer is either true or false. So if you can recall the scaling phenomena, you can figure out that when you scale something, then the coordinate points of the original objects actually change. So why? Because you multiply the original coordinate values with the scaling factor. So the answer for this question is true. If scaling factor is greater than 1, then the object size is going to increase, decrease, or remain unchanged. Now, again, the answer is encrypted in these equations. Now, you can imagine what will happen if this scaling factor, this Sx, Sy, and Sz, are greater than 1. That means when you do this multiplication, you will get some value which is going to be greater than this x0 if Sx is greater than 1. So in that sense, when the scaling factor is greater than 1, the object size is going to increase. So correct answer is the first option. Third question. If scaling factor in 3D are Sx, Sy, and Sz along x, y, and z axis respectively, then in scaling matrix, the item at 1, 1 location is, for this you have to go to the scaling matrix itself. So this is your scaling matrix. Now let me put the subscripts for the two-dimensional array. First column 0, 1, 2, 3 along the columns. Then this is the first row with subscript 0, then 1, then 2, then 3. And the question was asking you to figure out the item at location 1, 1 into the scaling matrix. Now, from visual inspection, you can say that the item at location 1, 1 is SY. So the correct option is the second one. Now, fourth question. Suppose you have a point 2, 2, 2. You apply scaling by the scaling factors 3, 3, 3. Then the transform point will be, so you can arrive at the conclusion either from this set of equations or from this single equation. Your original point is 2, 2, 2 and 2. Now you apply scaling factors 3, 3 and 3 along x, y and z axis respectively. So after the transformation, the resulting point is going to be, now you can figure out, 6, 6 and 6. So the correct answer is the third option. The size of the reflected object is same as the size of original object. Now, this is again a concept from general physics. When you reflect something, then you get the mirror image of the original object. However, the size of the reflected object is not changed. It is same as the size of the original object because no scaling actually happens here. So the correct answer is going to be the first option. So yes, don't forget to write your university roll number into the chat box. In reflection relative to xy plane, which is true, x coordinate value changes, y coordinate value changes, z coordinate value changes. Now you are doing reflection with respect to the xy plane. So if the reflection takes place relative to xy plane, you can see that x and y coordinate values actually don't get changed. Only the z coordinate value changes. Z new equals to minus z old. So the correct answer is z coordinate value changes. In reflection relative to yz plane, which is true, the question is similar to the previous one. Now if the reflection is relative to yz plane, then you can figure out that you will get the image on the other side of the yz plane, and in that case only the x coordinate value will be changed. X new equals to minus x old. So Those of you who have not written your university roll number yet, next question goes like, if reflection relative to z explain, which is true? X coordinate value changes, y coordinate value changes, z coordinate value changes. Reflection is related to the z explain, so the y coordinate value will be changed. This question is somehow wrong. This question is not wrong actually. It should be if, not in. Typographic mistake. If reflection angle between original point and reflected point, no, that's right. In reflection, the angle between original point and reflected point is 90 degrees, 180 degrees, and 360 degrees. So for that, yes, you have to visit this image. You can see that the angle between the original point P and the reflected point P dash is 180 degrees. So the correct answer is 180 degrees. If you reflect a point 222 with respect to xy plane, the reflected point will be at, so the reflection is related to xy plane, only the z coordinate value will be changed. So you can say that the correct answer is 2 2 minus 2, where you can see that only the z value changed. So this was the discussion for today. One thing I must share with you is that a few days before I have submitted the CA3 marks, and this was the first time when I did not have to assume the marks randomly. I put whatever you have got yourselves. So go on studying like this. Hope you will do better than this sometimes in life. And another thing I would like to say is that I'm going to make the quiz live once again so that you can attempt it in future also. If you have faced some difficulty during the discussion, then watch the tutorial video which I'm going to upload after some time once again, then read the study